Hello everyone, welcome back. We are starting chapter 27 today. And chapter 27 is really just a continuation of the materials that we had in chapter 26, discussing resistance and resistivity. And in chapter 26, we derived the expression for the what I call the store-bought resistor value. Depends on the resistivity of the material, in other words, what it was made of, the length of the object and the cross-sectional area of the object. And then we also saw how temperature can affect the resistivity and cause the resistance of an object to either go up or down. And then we talked about power in terms of how a resistor can dissipate energy in the form of heat, and by using a combination of the first power equation, which we derived, along with the Ohm's law expression, then we have three different versions of that power expression that we can use. So now in this video, what we want to do is something very similar to what we were doing with the capacitors, and that is to see what's going to happen if we start connecting more than one resistor in the same circuit. And there are two main ways that we can do this. The first one that we have here, we have resistors 1 and 2 that are connected one after the other. By definition, that is a series connection. Over here we have our battery with a certain voltage value. But then we could also connect the resistors in parallel. And that definition is that we have to have the heads and the tails of the resistors connected together. From there, we can then combine them to a battery. And so in that case, we have our parallel system. What we need to do now is look at each of these systems in terms of how the charge that comes from the battery travels through the circuit. When we discussed the capacitor systems, we had charge that would come out of the battery, and that charge would deposit onto the capacitor plates. But in the case of resistors, our charge is going to travel through each of the resistors in the form of current, and ultimately end up back at the battery. And again, current, by definition, is the flow of positive charge. Now, looking at this first picture, we have some current that is coming out of the battery, but then that current has to go through resistor 1. And then that same current has to go through resistor 2. And this is going to be the first concept that we have for series resistors. We're going to say that resistors in series, actually we don't need to write all that out, resistors in series are going to have the same current. When we hook resistors up, we're still allowing charge to flow through the material. It's just that that material is regulating the rate at which that charge can flow through. And so having one resistor connected to another would be like having two garden hoses of different sizes hooked together, one after the other. And based on the diameter and the length of each hose would be able to move water through it at a different rate. Obviously, the hose with the wider diameter would be able to move more water through it. But any water or current that enters is really going to be limited by the smaller of the two resistor values. So whether I had the large hose connected second or first, it would be the smaller hose, which is providing a higher resistance value, that would ultimately determine how much current can flow through the entire system at once. So again, we use a water analogy. I've used a number of water analogies here with our chart and circuits just because it works so well. But now we know that these two resistors will have the same currents. And if that's the case, we can drop the subscripts. We can say that each of these resistors is going to be using the same current of I. From there, we can use Ohm's law to help us define the potential difference that exists across each of those resistors. So resistor 1 will have a potential difference that we can call V1. Likewise, resistor 2 will have a potential difference that we can call V2. V1 will equal the current I, which passes through resistor 1. V2 will equal I times resistor 2. Now, why is it important that we know the potential difference across each resistor individually? Well, that is so that we can account for the potential difference across the battery. The potential difference across the battery is V, and we can accomplish that potential difference by moving from one point to the other. The easiest way to do that would be to just go across the battery, but that's not our only choice. We could also go all the way through the circuit. And that means that the combination of the potential differences across each resistor combined will have to equal the potential difference across the battery. And so that means we can take the combination of our two potentials, we can add them up, and this is going to be the basis for our ability to find an equivalent resistance for the circuit. This was a really big idea back in our capacitance chapter. We wanted to be able to take all the capacitors in a circuit and replace them with one capacitor that would do the same job. Well, now we want to do that with the resistors. I want to remove resistor 1 and 2 from that circuit, and I want to replace it with one equivalent resistor that will do the same job. What do we mean by the same job? Well, we mean that this equivalent resistor should draw the same amount of current from the battery. Ohm's law says that V equals I Req. the potential, excuse me, the potential across the equivalent resistor has to be the potential across the battery, because that's the only thing that is connected to the battery, is that equivalent resistor. So our equivalent resistor has the same potential as the battery, but we said that the potentials of battery 1 and battery 2 have to add up to the potential of the battery. So let's make a substitution there. The potential of resistor 1 plus the potential of resistor 2 has to equal IREQ. But while we're at it, let's substitute the values of V1 and V2. V1 is IR1, V2 is IR2, and that equals IREQ. Now we can see that the current that is running through our circuit doesn't matter, because we can find the equivalent resistance of the circuit just by taking a direct summation of the resistors that are connected in series. So how does that help us? Let's put some numbers to this. Let's say that our battery was 100 volts. Resistor 1 is 50 ohms, and resistor 2 is 150 ohms. So I would like to know everything that there is to know about this circuit. I would like to know the current that is coming out of the battery, and hence the current that is running through each of the resistors. I would like to know the potential difference across each resistor. I would also like to know the power that is associated with each resistor and how much energy the circuit is dissipating. And so I know that sounds like a lot of stuff, but we can do this. We already know that two resistors that are added in series can be replaced with an equivalent resistor that is equal to their summation. So the equivalent resistor for this circuit is going to be 200 ohms. The current that comes out of the battery is I. V equals IR. In this case, R equivalent. That means that I is equal to V over REQ. We have a 100 volt battery and 200 ohms for the equivalent resistance. And so we're getting a current that is equal to half of an amp. Now that we know the current that is running through our circuit, we can apply that to the individual resistors. Don't need the subscript on the current term because it's the same current. V1 will equal the current times resistor 1. So we have a half times 50, which is 25 volts. There's V1. Now, we actually shouldn't have to do the math for V2, because we already know that the combination of V1 and V2 will have to equal the total potential that's coming from the battery. We know that the battery is providing 100 volts, and we know that we've already used up 25 of that on the first resistor. So there should be 75 volts left for the second resistor. This is our self-check. Well, let's check our work. We have a current of 1/2 an amp, and resistor 2 was 150 ohms. Well, 1/2 of 150 is 75. 25 and 75 equals 100. So we're done. We now know everything that there is to know about this circuit. We know what the resistor values are. If we want to, we can turn this into a table similar to what we did with the capacitors, and we can fill in the values that we have for each. We know that the current going through each of our resistors is 1/2 an amp. And from there, using Ohm's law, once we have 2 pieces of information, we can solve for the third. And this is where we get our 25, our 75, and our 100. Once the table is full, we can answer all of the other questions. Some of the other questions we had were, what was the power associated with each resistor? Well, you have 3 equations that you can utilize to find the power that is associated with any given resistor. We also wanted to know what was the rate that the circuit dissipated energy. And that entire phrase, the rate at which energy is dissipated. We talked about this in a previous video, and that entire statement is just a really fancy way of asking for the power. So we have this circuit, which is made up of a battery and 2 resistors, and those resistors are going to be dissipating energy in the form of heat. Well, the first resistor is going to dissipate heat based on its power value. The second resistor is going to dissipate heat based on its power value. So if I know the 2 power values of those resistors, again, take your pick, then I can add up those values and I have the total power of the circuit, which is the total rate of energy dissipation for the circuit. But why do so much work? Why find the power of each resistor individually if we just want to know the power of the entire circuit? In that case, why not use the information about the equivalent resistor? Because it is the job of the equivalent resistor to do the same thing as what all the other resistors in the circuit are doing. And that includes dissipating energy. And so we can take any one of these equations here to solve for the energy dissipation of the circuit. And I'm just going to go with the first one here. The current going through the equivalent resistor is 1/2 an amp. The potential associated with the equivalent resistor is 100 volts. So 1/2 of 100 is 50. And that pretty much finishes everything that we can do in terms of the series resistors. We're going to go ahead and put together some notes up here concerning the series resistors. We'll say resistors in series have the same current but have different potential values. And that we've already seen We've already shown that. There were different potential values for the two resistors. And we have a means of finding the equivalent resistance just by taking a direct summation of all the resistors that are connected in series. So now we need to see what's going to happen if we connect our resistors in parallel. And then we'll bring whatever notes we come up with from there. So I'm going to take the parallel drawing that we had here, and we'll bring it down to some of the open space that we have. And we'll just redraw this. So we have resistor 3 and resistor 4. Now, based on how a circuit is drawn, there are a lot of ways that a circuit can be drawn, but the really important part is where things are connected, and that is what determines whether or not a resistor is in series or in parallel. Right here, it's pretty easy to tell that these resistors are in series. I'm going to move the screen over so that we can't see the battery for right now, but we can see that the heads of each resistor and the tails of each resistor are connected at the indicated points. So they are in parallel. But I'm going to draw this same circuit in a slightly different manner. So, believe it or not, that is the same circuit. If we look at where the heads of each resistor are connected and where the tails of each resistor are connected, it's the same picture. I just have an extra length of connection between the tail of resistor 4 and where it connects to the tail of resistor 3. Another way that I could draw this, we could have something that looks like this. Resistor 3, resistor 4. This is the same picture as the other two. We have the heads of each resistor connected at the same point. We have the tails of each resistor connected at the same point. And if you consider how the battery is connected in each of these pictures, the head of the battery is connected to the heads of the resistor. The tail of the battery is connected to the tails of the resistor. Let's try the next picture. The head of the battery is connected to the heads of the resistors. The tail of the battery is connected to the tails of the resistors. So these are the same pictures. And finally, for this third picture, the head of the battery is connected to the heads of the resistors, and the tail of the battery is connected to the tails of the resistors. So we may see circuits drawn in different ways, and at first it may not necessarily look like a set of resistors is connected in parallel or even in series, but it's our job to really look at where those resistors are being connected. And the fact that there is nothing else connected in between means that we do in fact have a parallel system for our resistors. Now we only need one version of this picture, so we'll go with the first one there. We've talked about parallel systems before with our capacitors, and very much like the capacitor circuits that we saw, everything up here is just one big point of connection. Everything up there has the head of the battery connected to the head of resistor 3, connected to the head of resistor 4. So everything up there is just one big point of connection. Likewise, everything down here is just one big point of connection. And so everything between those two lines will have the same potential difference. We already know what that potential difference is going to be because we have the battery. This means that the battery is directly connected between resistor 3 and resistor 4, and so each resistor will have the same potential value. The potential of resistor 3 will equal the potential of resistor 4, which is equal to the potential of the battery. Now, I haven't given any numbers yet, but we don't need the numbers to make that recognition there. So that's our first concept for the resistors in parallel. Resistors in parallel will have the same potential. And again, I'm going to try to. Let's zoom in and see if we can do that. There we go. I'll move the screen over just a little bit so that we can't see the battery. But even though I can't see the battery, that doesn't change the fact that resistor 3 and resistor 4 have their heads and tails connected at the same points, so they will share the same potential difference. In this case, it just happens to be the potential of the battery. But for other circuits, you may not have those resistors directly connected to a battery. Well, if these resistors have the same potential, what's going to be different about them? Let's find out. Let's zoom in on our circuit here. Our battery is the source of our current. Once we hook the battery up to these resistors, the battery starts providing current to the circuit. But then that current gets to this intersection, and the current has to make a choice. Does it go through resistor 3 or does it go through resistor 4? And the answer is yes, because it's going to go through both of them. But only a portion of the total current will go through resistor 3, and we're going to call that current 3. The other portion of the current will go through resistor 4. We'll call that current 4. And we now have a mathematical expression. The total current that comes out of the battery is responsible for providing current 3 and current 4. And then when current 3 and current 4 get down to this intersection right here, they will have to recombine to produce the total current once again. So our resistors have different current values. Now we want to see, can we make an equivalent resistor? And for any circuit, we should be able to produce an equivalent resistance. And this equivalent resistor is supposed to do the same job as what resistors 3 and 4 are doing with their current combination. So what do we mean by doing the same job? Well, we mean that we want that equivalent resistor to draw the same total current from the battery. V equals IR, in this case I total and R equivalent. This potential here, the potential across the equivalent resistor, is the potential of the battery, which is the same as what we have up there. But it really doesn't do us much good to take that value up there, because resistor 3 and resistor 4 don't have the same current values running through them. Not only that, I don't have any numbers in front of me right now, so I can't try solving for anything. Instead, what I could do is I could rearrange this equation for the total current. The total current that is provided to the circuit will have to equal the potential of the battery divided by the equivalent resistance. And that can go into our, this is what we would call a conservation of current equation. Basically, whatever current enters a node or an intersection between wires, whatever current enters has to equal the amount of currents that exit that node. And we already have that idea established. But now we can start bringing this information together. We know that the total current coming out of the battery has to equal V over Req, which has to equal the current passing through resistor 3. Well, let's find that. V3 equals I3 R3. But we already know that the potential difference across resistor 3 is the same as the potential difference across the battery. And that means that I3 is equal to V over R3. So we'll plug that in to our equation. And then we just need I4. Well, the potential difference across resistor 4 has to equal the current traveling through resistor 4, but the potential difference across resistor 4 is the same as the potential for the battery and resistor 3, and that means that current 4 has to equal V over R4, and that will be plugged in right here. And now we can see that the potentials for each term are going to cancel out. And we're left with 1 over the equivalent resistance equals 1 over R3 plus 1 over R4, or 1 over the equivalent resistance can be found by taking the summation of the inverse resistance values. So let's take that along with the side notes that we had there for our resistors in parallel, and we'll put it up here with the notes that we had for series. So resistors in parallel have the same potential, have different current, and we can find the equivalent resistance by taking the inverse summation of all the individual resistors that are connected in parallel. And now we'll go ahead and plug some numbers in. For our parallel resistor circuit, let's use, I'm going to get rid of this stuff now, since we have all of the math established. We can go ahead and use it. We need a value for the battery, and we need a value for each resistor. We'll say the battery is 25 volts. Resistor 3 will have a value of 10 ohms, and resistor 4 will have a value of 40 ohms. And just like the other resistor problems, I want to know everything that there is to know about this circuit. So I want to know the current going through each resistor. I want to know the potential associated with each resistor. I want to know the equivalent resistance of the circuit. So if we need to, we can make ourselves another table. The potential across each resistor is technically already known. The battery is directly connected to each. So each resistor has a potential of 25 volts. Ohm's law is how we're going to shift back and forth between all the different values and solving for the missing pieces. In this case, each resistor is going to have to use this equation. The current traveling through resistor 3 will equal the potential of resistor 3 divided by the resistance of potential 3, which is 2.5 amps. For resistor 4, the current traveling through resistor 4, we need to take the ratio of our potential, which is now 25 over 40. And so 25 divided by 40, put this into my calculator, is 0.625. Now that I have the individual current values for resistor 3 and resistor 4, remember that the total current coming from the battery has to be the combination of those two. 0.625 plus 2.5 makes for 3.125, which in the case of the equivalent resistor, so if we redraw this circuit utilizing an equivalent resistor, that would be the battery of 25 volts connected to an equivalent resistor. I now know that the total current that has to come out of the battery is 3.125 amps. I know that it's coming from a battery of 25 volts. We can then use Ohm's law to tell us what the equivalent resistance value for this circuit should be. And so now we have 25 over 3.125. 25 divided by 3.125 is 8. Well, can we reproduce that? Can we figure out what the equivalent resistance of this circuit is without actually going through and solving for it using the individual information about current and potential from each resistor. Well, our potential notes say that we should be able to find that equivalent resistance by taking the inverse summation of our resistors. So the inverse value of our equivalent resistor should equal the inverse summation of the resistors. We have 1 over 10 plus 1 over 40. And let's see here, that would be 5 over 40. But that's not our answer. That is the inverse of our answer. To get our answer, we have to flip over both sides, and 40 over 5 is 8. So that is correct. Again, I will remind you that for future circuits problems, you may not have the luxury of knowing what the potential difference is across your resistors. In this case, we did. They were both connected directly to the battery. We were able to use those values to help us solve for stuff, but for some future problems, you may end up not knowing exactly what your resistor is hooked up to. Okay, we're going to end this video right here, because what I want to do in the next video is start looking at combinations of resistors in a circuit. So what do we do if we have more than one resistor in a circuit? What do we do if it looks like there's both series and parallel combinations? Well, we're going to do the same thing that we did with the capacitor circuits. We're going to go through a piece at a time, combining the circuit, looking for either parallel or series combinations. We will eventually reduce the circuit down to an equivalent, and then start backtracking our way to the original diagram, all the while making sure that we keep track of all of our resistance, current, and potential values in a table. And that table is going to be what saves us, because these problems, as we've already seen with the capacitors, there's a lot of steps, there's a lot of repetition, and it would be very easy to misplace a value somewhere along the way, and everything has to fit perfectly in these circuit problems in order to get the correct answer. And so one little slip up is going to be fatal to our attempts to solve these problems. And then in addition to looking at a problem like this, we need to consider what happens if we have more than one battery in a circuit. So if you have more than one source of electric charge in a circuit, how is that going to affect the function and the behavior of everything else that's in the circuit? So that's what we'll do in part 2. We'll see you there.